Hi everyone, welcome to my YouTube channel Edu-spectra. My name is George. So today we will be continuing with our class 9 chapter number 1 number system. In our previous class we had learned about the different types of numbers which are natural numbers, whole numbers, integers and rational numbers. So today in our class we will be starting with irrational numbers, which is also a entirely different class of numbers. So in a lower classes and in a previous class we had learned about rational numbers. What were rational numbers? Rational numbers are those numbers which can be written in the form of p by q, where p and q are integers and q not equal to 0. Now the topic that we will be learning is about irrational numbers. So in the name itself you can see that is irrational numbers. So what could irrational numbers be? Irrational numbers are those numbers which cannot be written in the form of p by q, where p and q are integers and q not equal to 0. So irrational numbers are just the opposite to that of rational numbers. Okay, now what are the examples to them? The examples to irrational numbers includes root 2, root 3, root 5, pi, 0.1011, etc., etc., etc. Okay, basically if you see over here, all the imperfect roots can be considered as irrational numbers. Pi, whose value is 3.14, is also a irrational number. Similarly, this is also an irrational number. Now, why did I write only imperfect roots are irrational? What about perfect roots? For example, let us take root 4. Okay, we know what is the value of root 4. We know root 4 is equal to 2. So now we observe over here, what is root 2? Root 2 is, root 4. Root 4 is 2. So here we have got a rational number. Okay, root of 4 is equal to 2, which is a rational number. So we cannot consider perfect roots as irrational number. Similarly, if I write root of 9, we know root 9 is equal to 3. Okay, so such perfect roots cannot be considered as an irrational number. Okay, now one small thing which I would like to mention here is that from our ninth standard, whenever we write a square root of 4, we should always write it as plus or minus. Okay, this is the symbol that we use. Okay, we put a plus and below that we put a minus. It is read as plus or minus. Okay. Now, why you may ask me, why are we writing plus or minus 2? I will tell you the reason. We know square root means we have to square something. So let us take 2 over here. So we know 2 square is equal to 4. That is square root of 4, we will be getting it as 2. Now, if I ask you what is minus to the whole square? Minus to the whole square means what? Minus 2 into minus 2. Okay, minus 2 into minus 2. What is minus 2 into minus 2? We still get a 4. So, either positive 2 or minus 2 can be the square root of 4. So, from our 9th standard onwards, whenever we write the square root of any perfect roots, we should always write it as plus or minus. Okay. So, if I ask you what is the square root of 25. Okay, if I ask you what is the square root of 25, how will you write it? You should write plus or minus 5. If I ask you square root of 36, how will you write? Plus or minus 6. If I ask you how to write square root of 49, how will I write? Plus or minus 7. If I ask you square root of 64, we will write it as plus or minus 8. Okay, why? Because minus 8 the whole square plus 8 the whole square both gives you 64. 6 the whole square minus 6 the whole square gives you 36. 5 the whole square and minus 5 the whole square also gives you 25. Minus 7 the whole square and plus 7 the whole square also gives you 49. So I hope I am clear with this concept. Now, how will we identify whether a given number is a rational number or an irrational number? This concept we will be seeing a bit later. So you just note down the examples for irrational number as of now. It includes all the imperfect roots. Perfect roots are not irrational numbers. They are rational numbers. Similarly, pi is an example of an irrational number. 0.1010 etc. etc. is also a irrational numbers example. Now, one small interesting fact which I would like you to tell is about the discovery of irrational numbers. Actually, before I tell you, I hope you might have heard about the great mathematician Pythagoras. Okay, actually Pythagoras was a great influencer. He was a person which many people admired. They thought of him as a spiritual leader and all. So actually, according to Pythagoras, all the numbers in this universe are rational numbers. There was nothing called as rational numbers. But a Pythagorean named Hippacus, you can see a Pythagorean named Hippacus, he was also a follower of Pythagoras. He discovered that he could not express root 2 in the form of p by q. So he told that not all the numbers in this world are rational. There are certain numbers which are also irrational numbers which cannot be written in the form of p by q. But the one myth, it is like a myth, okay? It is said that many people who believed in Pythagoras did not want this Hippacus to say something against their beliefs and all. So he was drowned in the sea to death by these Pythagorean people. So you can see over here he is drowning. So if anyone finds any more such legends or any myths, they can definitely share about it in a chat box. So it was Hippacus who is considered to have discovered about irrational numbers, but he had an unfortunate death. Okay, let us just check what all have we learned. Okay, now we have learned about various different classification of numbers. We classified numbers into natural numbers, whole numbers, integers, rational numbers and irrational numbers. Now, is there a big class or is there a king that we can call of all these numbers? Yes, we can call the king of numbers as real numbers. So actually, under the real numbers, the entire set of numbers that we learn now belongs to. So if you see, the real numbers is like the king. It consists of rational numbers and irrational numbers like we said, and we had also said that rational numbers can be an integer, it can be a whole number, also it can be a natural numbers. So if you look in a particular way, that all the numbers which are present on a number line or all the numbers which are existing in this universe belongs to the category of real numbers, and real numbers consist of two subdivisions, that is rational numbers and irrational numbers, where rational numbers can be expressed in the form of p by q, which consists of integers, whole numbers and natural numbers, while irrational numbers cannot be expressed in the form of p by q, and it is the other set of classification of numbers. I hope I am clear with it. Okay, if anyone wants, they can make a note of this flowchart. Okay, so now let's move on to our next topic, which is decimal expansion. Okay, so we are learning how to solve division or how to do divisions from lower classes itself. So now let us notice a particular pattern over here. Just notice when we do 10 by 3, okay, I have done the division here for you. We see here that this 10, 9, 10, 9, 10, 9 are repeating and going, and finally we get remainder 1. Okay, so here we know when we do 10 by 3, the 3 here, 3 is the divisor, 10 is the dividend, and we are getting the quotient as 3.333 and it is going on like that. So um, that was the first case and we are getting the remainder 1 for every time we do a division. Okay, similarly here you see, here also I have written 7 by 8. Here we observe that in this particular division we are getting our remainder is equal to 0 and we are getting the quotient as 0.875 and here I have written the expansion of root 2 and pi. Okay, now let us see what is the pattern that we are able to see over here. Okay, just see over here, when we did 10 by 3, we got our quotient as 3.33. That means when you are doing 10 by 3, the answer that you will be getting is 0.333 etc. Oh sorry, 3.33 and it is going like this. Okay, so we see here that the after the decimal point the number 3 is repeating and going. So usually this 3 is repeating and going, so we usually represent this as 3.3 bar. Okay, we put a line over that 3 in order to represent that this 3 is repeating. We call this dash or this symbol as bar. So it is read as 3.3 bar. For example, if I write 2.171717, it is going on like that after the decimal point. So how will I write it? I can write it as 2.17 bar. Okay, so that is the meaning of bar. Bar means on whichever number the bar is present, that number is repeating and going after the decimal expansion. So here you see, when we did our long division, we saw that we got 3.3333 etc. as our answer. So whenever after the decimal point any particular number is repeating and going, as we saw over here in 3.3 example, when we did 10 by 3. So here when we did 10 by 3, we got our answer as 0.3 bar. So if this number after the decimal is repeating and going, such decimal expansion, we call it as non-terminating repeating, otherwise non-terminating recurring decimal expansion. I hope I am clear. That is terminating recurring, or also we can call it as non-terminating repeating. Both the usage are correct. Okay, so I hope I am clear. When we did 10 by 3, we got a quotient as we got a quotient as 3.3333 and it is going on like that. So whenever something is repeating, we usually put a symbol of bar over it. So and we told that since this number is going on like this, we call it as non-terminating repeating. Okay, now look at the second example, that is 7 by 8. When we did 7 by 8, we are getting the answer as 0.875 and we are getting the remainder as 0. So here we observe that at a particular place our answer is getting stopped. Okay, basically we can say that after the decimal point there is an end to the numbers. Okay, where here basically we can see an end. Okay, so in such cases when there is an end to numbers after the decimal point, we call them as terminating decimal expansion. The word terminating means stopping. So when I did 7 by 8, I am getting my answer as 0.875, which is stopping. Like here we saw that the 3 is repeating and going and it is going on forever like this. But here the decimal, after the decimal point the numbers are stopping. So such decimal expansion we call it as terminating decimal expansion. Okay, terminating decimal expansion. So I hope I am clear with this topic. That is when we did 10 by 3, we got 3.3 bar. That is after the decimal point, the number is going on. The same number is going on, repeating and going. And here also in terminating decimal expansion, after the decimal point, there is a stopping to that numbers. Okay. Now the next thing which I have written is the expansion of root 2. So in your 8th standard you have learned how to find the value of square roots and all. So I have written it for you. The value of root 2 is 1.41421356 etc. And pi we know. It is 22 by 7. So when we do the expansion of 22 by 7, we are getting the answer as 3.1415925 and it goes on like it. Now, here we observe that after the decimal point, the numbers are repeating, but there is no particular order in which they are repeating. Many random numbers are written after the decimal point, and those random numbers are just repeating and going. Okay, so such set of numbers we call them as non-terminating, non-recurring, otherwise non-terminating, non-repeating. Okay, so now just observe over here what is the difference between non-terminating repeating and non-terminating non-repeating. In non-terminating repeating, the same number, for example, when I did 3.3 bar, this after the decimal point, this 3 itself is repeating and going. If I say, for example, 2.27 bar, what does it mean? It is 2.272727. That same number is repeating and going here. But in non-terminating, non-recurring or non-terminating, non-repeating, some random numbers, it does not need to follow a particular order. It is simply repeating and going till infinity. So that is the difference between non-terminating, non-repeating and non-terminating, repeating. Now, terminating, I hope you understood it is very much clear that if they after a particular point, if you can see there is a stop or if there is a stop over there, then it definitely will be terminating. So now, how will you identify whether a particular number given to is terminating, non-terminating, recurring or non-terminating, non-recurring? Just see, in terminating there will be no dots, nothing. It will be a clear cut stop over there. If it is non-terminating recurring, you should see that if there is any number repeating like this, like 2727, is it repeating and going like that in a particular order, or you should observe if there is a bar symbol above it. If there is a bar symbol, then definitely it is non-terminating, repeating. And if it is non-terminating, non-repeating, they will simply write many numbers after the decimal point and put dot dot dot. Then it will be definitely non-terminating, non-repeating. I hope I am clear till here. I would like to discuss a very important topic right now. Now, in your exams, they can give you a few numbers and they can ask you whether it's a rational number or an irrational number. So how will you identify whether the number given to you is a rational number or an irrational number? So you can make a note of it, that is every terminating and non-terminating repeating numbers which are having the decimal expansion are always a rational number. That is, terminating and non-terminating repeating decimal expansions are always rational number. I will write it for you. The terminating and non-terminating repeating are always rational. Okay. So similarly, if the decimal expansion is non-terminating, non-repeating, it will be irrational. Okay. If it is non-terminating, non-repeating, then definitely it will be an irrational number. So you can see over here. For example, if you see 10 by 3, 10 by 3 can be written as 3.3333 etc., which is a non-terminating recurring, and you know 10 by 3 can be written in the form of p by q. So definitely this will be a rational number. Similarly, 7 by 8, if you see this 0.875, we know 7 by 8 can be written in the form of p by q. Even the decimal expansion is terminating decimal expansion. So definitely 10 by 3 and 7 by 8 is is a rational number. But if you see over here, when we do pi we know 22 by 7. When we are doing 22 by 7, the answer we are getting it as 3.1415925, and it goes on like that. So if it is non-terminating, non-repeating, then definitely it will be a irrational number. That is the reason why we consider pi root 2 and all as irrational number. So this is the way in which we identify a particular number given to is rational or irrational. Just check whether it is terminating, non-terminating, repeating, or non-terminating, non-repeating. I hope I am clear with it. Please make a note of it. Okay. Before we move further, I would like to tell you a few notes. That is the value of root 2, root 3, etc. Okay. It is nice if you by heart these values because you may require them in higher classes. So the value of root 2, if you see, it is 1.41. But just now before we saw that the value of it is 1.41, etc., etc., and goes like this. But for mathematical calculation and for simplicity, we can just write it as 1.41. Similarly, value of root 3 is 1.73, and we know square root of 4, we know it is 2 square, which is 2, which is 4, so square root of 4 is equal to 2. Now, you just observe a pattern over here. We saw that square root of 4 is equal to 2. Then definitely square root of 3 will definitely be less than 2. That is, so square root of 2 and square root of 3 will be 1 point something. So similarly, if I ask you what is square root of 5, definitely it will be 2 point something. Okay, it will be a number greater than 2. So the exact value of it is 2.23. Okay, so the value of root 2 it is 1.41. Root 3 it is 1.73, root 4 you know it is 2, and root 5 it is 2.23. So it will be nice if you remember the value still root 5, because it may be useful for you in your higher classes. Okay, now we will move on to our exercise number 1.2. Okay, so here the question number 1 is state whether the following statements are true or false. Justify your answer. Okay, so the first question is every irrational number is a real number. Yes, definitely every rational numbers are real numbers, because if you remember the flow chart I had drawn, we had drawn it like this. Real numbers can be divided into rational and irrational. I had told you real numbers is like the king. It is the largest among all the numbers, or it is the set of numbers which consist of everything, both rational and irrational number. So we can say that every rational number is a real number. So it is definitely a true statement. Okay, it is definitely a true statement. Now our next question is question number 2. Every point on the number line is of the form root m, where m is a natural number. So the answer to it is false. Why is it false? Because if you see a number line, we know here we are having 0, 1, 2, 3, 4. Here we are having the negative numbers minus 1, minus 2, etc. So is every point on the number line of the form of root m? No, definitely no. Why? Because on the number line we cannot always have irrational numbers. Root m, it is not possible. It also includes a whole number, natural number, and integer also. Similarly, if you ask me what is root of minus 2, okay, it is not defined. Actually, it is something which we call it as complex numbers and all, which we will be learning in your class 11. Okay, similarly, not every point on this number line can be written in this form, because root of -2 is not defined, but which you will be learning in your higher classes as complex numbers and all. So definitely every point on the number line cannot be of the form root 10. So definitely it is a false statement. Okay. Now the third question is, every real number is a irrational number. Again, it is a false statement. Why is it a false statement? Just now we said that real number consists of both rational and irrational numbers. So we cannot say that every real number is an irrational number. Every real number can be rational and irrational. So we cannot specify and say that every real number is a irrational number. So that is a false statement. Okay. Now we will move on to our question number 2. So our question number 2 says that, are the square roots of all positive integers irrational? If not, give an example of the square root of a number that is a rational number. This is exactly which I had told you when I had given to you the explanation. For example, if I take root 2, we had written the value as 1.41 etc. and it goes like this. That is 1.412 1, 3, 5, 6 and it goes on like this. Now, they are asking you, are every root numbers or are every roots irrational? No. I had told you in the beginning also, all the imperfect root numbers or the imperfect squares are irrational numbers. But if I say root 4, what is the answer for root? So if you see here, we got root 4 is equal to 2. So what is root 2? So here this 2 we can definitely write it as 2 by 1, which is definitely in the form of p by q. So we cannot say that every square root numbers can be irrational numbers. Only the imperfect roots are irrational. Perfect square roots are only irrational. If I say about root 4, similarly if I ask you root 9 which is equal to 3, it can also be written in the form of p by q. So definitely all the square roots of positive integers definitely cannot be a irrational number. Okay. So you can also make a note of it, that is perfect squares are not irrational numbers, they are rational numbers. That is, always all the imperfect square roots are irrational while all the perfect square roots are rational. So the question to that is no. And you can give the example of root 4. Okay, because root 4 is an example of a square root which can be written as a rational number. So that is what they are asked you in the question. The square roots of all positive integers are not irrational, and the example that you can give is of root 4 or root 9 or any other perfect square root. Okay, are examples. Okay, so that's all that we will be discussing today. I know there are question number 3 and 4 also in the exercise. Those I will be discussing when I teach you the operations of real numbers. We will do those questions there. Okay, that is, thank you. Please like, share and subscribe the channel.